This slide introduces the DFT equation. The DFT equation basically is to calculate the DFT coefficient x, and we does it by left multiplying the time vector, the signal vector x, by the DFT matrix W. You will see the notation or this equation often in textbooks, where xk is the element-wise coefficient of x, where k is equals to 0 to n minus 1. And this is the form that everyone will show you. Xn is the element-wise vector of the time signal from n equals to 0 to n minus 1. And W, a subscript n, kn, is the DFT matrix. Now, what you realize is that the element-wise of W n kn is e to the power minus j 2 pi n kn, where this is the kn, and you realize that the minus is defined here. And now you compare it with the equation 2 page before. Here, Wn minus kn, that's why the minus disappear. So, in brief, the difference between DFT analysis and synthesis equation is this. In the synthesis equation, we are trying to get back our vector x, the time sequence, from the frequency representation x, left multiplying by the inverse DFT matrix, scaling by 1 over n. In the analysis equation, we are trying to get the frequency representation, capital X, given that we are sending the time sequence vector x and left multiplying by the DFT matrix. There's no 1 over n here. And more importantly, the DFT matrix W and WH is differ by this negative sign here in each of these elements. This negative sign, as you know, will introduce the complex conjugate element in every W. So let's now look at the W matrix, the DFT W matrix. Each of these elements now have a negative values. So this is one big difference between W and WH. Let's now study this equation from this representation for element-wise to a vector matrix representation. Again, I have color-coded it. The blue is to represent the frequency representation. The yellow represents the DFT matrix. The green represents the time vector. Here we see the representation of the frequency representation in vector form. K goes from 0 to n minus 1. So as we are going down each row, we are increasing k. So this is index k from 0 to n minus 1. So therefore, along this big matrix, we're also going along k here as we are going down the rows. And what about this vector? This is, of course, the time vector. Time goes from x small x0 to x n minus 1. What about this W matrix? Now we insert this element, or this element, WKN, we substitute different k and different n, and then we get what do you get? Well, the difference is that there is a minus sign here. So as we are going down the rows, we're changing k's. As we are moving along the column, we're changing n. Because now you must be thinking, this DFT matrix, the horizontal row, this row is going to multiply by this column to get the first element. So this element is the inner product of this row. Well, should be the multiplying of this row and this column. The second entry is this row multiplying by this column. And you'll realize that this operation, this xk, can be thought of as the inner product of the small x vector with column k of wh. Now, go and look at the wh. So let's look at this column. Let's say w, the column, this column 1 of wh. And when we want to perform the inner product with this column, we have to transpose this column and conjugate it. So we put all the minus sign. Now you look at this column now. It's exactly column 1 of wh. That is transposed and conjugated. So the relationship between wh and w is very close to inverse. Let's see why do I say that. wh times w is n times I. What is n? N is the constant. And what is I? I is of course the identity. And 0. What is the size of this I? Is the dimension is n by n matrix. So wh and w is almost an inverse of each other. And why is this so? Well, first is we told you that the columns of w are orthogonal. So when they're orthogonal, of course, it will produce all these zeros that are that when we try to inner product different columns together. But when we try to inner product by itself, since each element of w has magnitude 1, when we try to perform this inner product by its own column, when j equals to k, we'll get a value n. And this is why the diagonal of this element is n. So if you really want to put it this way, then we should do it this way, as each of these n of each of this element in the diagonal is value n when we multiply wh by w. Okay, so this is the property when the w's have orthogonal columns and the elements of w all has magnitude 1. So you look at this, all the elements have magnitude 1. This is 1, and then the only difference is that the value of the phase in each of these elements is changing. We're almost done, so maybe let's just very quickly recap what we are doing. This is the important slide for the DFT analysis equation. In the DFT analysis, basically we're giving to the system X the time sequence, the discrete time sequence as a vector. This is Rn. We are left multiplying this by a W, which is an n by n complex matrix. And then out comes the DFT coefficients, and typically we call it the big X. And this vector is complex and its dimension n. So this is the DFT coefficients on the left, and this is how we calculate it when we multiply the matrix by this vector. This is the compact representation that you find in most books, and I've color-coded yellow, green, and blue for you to see them in the 3 different forms. What is important now is to interpret what the rows of W is doing, because you'll realize that to get the first element or the second element or the kth element, to get this k equals to 1, we are multiplying this vector with this vector. We are inner producting this vector with this vector. Well, we are dot producting this vector with this vector. That's what we are doing. So in the next slide, we'll show you what does this vector look like. Thank you.